Welcome, everyone. It's actually great to see so many people. I wasn't expecting so many people after 2 years of, well, 1.5 years of the pandemic. Last time I gave this lecture here, it was, I think, early March 2020. And I was talking about coronavirus at that time. We'll talk about that a little bit also today, but hopefully we're done, but I'm not sure if we're done really. So we should still be cautious, I think. Science has not decided that this is done yet. Okay, but anyway, let's get started. It's great to see everyone, as I said. Are there people in the other room also? I think I see some people over there. So I cannot interact with you guys, but hello. Okay, so hopefully you're here for digital design and computer architecture, which is a bachelor's second semester course. Hopefully many people are in that situation. There are always a small fraction of people who are not in that situation. They may be visiting. Everybody's welcome. So let's get started. I mean, I have a lot of slides actually. This lecture is the fun lecture, let's say. We're not going to do a lot of technical stuff. This is an introduction. My goal is to give you an introduction of my philosophy of teaching and research and life in general. And also give you an introduction of what's happening in computer architecture today. Because today, 2021, 2022 is actually a very exciting time to be doing computer architecture. It was not the case, let's say, 20 years ago, 30 years ago or so. But today we're having a lot of issues, including the reliability issues that we observe right now. But there are other issues that we're having today that we will see. So hopefully you'll share my excitement. But again, this lecture, you don't need to take notes or anything. You can feel free to relax and enjoy the lecture. Okay, some people are already doing that. That's good. And you can see that this is already not working again. But I know the reason, I think. Okay, now it's working. That's good. Okay, so let me introduce myself quickly. I'm a professor here. I've been here for about 6 years or so. I think this is the sixth incarnation of this course. Last 2 incarnations were actually online. Well, the 2020 incarnation switched to online very quickly, but 2021 was fully online. Before coming to ETH, I was a professor at Carnegie Mellon University in Pittsburgh, USA. I was there for about 7 years, or actually I stayed there longer than I was physically present there. Before that, I started the computer architecture group at Microsoft Research, which is one of the premier research labs in industry. And I was there for 2.5 years or so after my PhD. During this time frame, I also worked at Google, VMware, Microsoft Research, of course, Microsoft, Intel, and AMD. So we do a lot of interesting work with industry as well. So I will hopefully give you some stories about what happens in industry, because there's a lot of exciting things that goes in industry also, in addition to academia. I got my PhD from University of Texas at Austin in 2006. If we have time, we will get to issues like prefetching in modern microprocessors. I developed some methods for prefetching in modern microprocessors that is employed in some of the microprocessors that you may be using today. We cannot tell exactly which one, but you may see traces of it. And before that, I was a bachelor student just like you at the University of Michigan. I did 2 degrees, computer engineering and psychology, and I graduated in 2000 or so. That makes me feel old now. You guys are just starting. Anyway, at some point you'll be like this also. So everybody gets old at some point, right? Okay, you can reach me. You can find out more about me and our work in this website. I guess I should be using this so that other people can see. And you can reach me via my email. My email tends to be very unreliable, and I get a lot of email. So please feel free to send another email, and also CC other people in the course if you would like to really get a response. If you just send a one-shot email, so it's like machine learning models today, right? If you see one cat, the machine learning model cannot realize it's a cat, right? My email is like that. If I get one email from one person, I don't realize that email, potentially. Of course, hopefully I'm not as bad as machine learning models of today, but I don't need to see millions of cats to understand that something is a cat. I think I'm a little bit better in my email than that, but hopefully this gives you an idea of how bad machine learning models today are. It has to see a million different types of cats to understand that something's a cat. And maybe we should be questioning that. And I think that's my main mission in this course, to make you question things, to think critically. Maybe nothing else matters in this course, but giving you that idea that you should be questioning everything and thinking critically is the thing that I most value that you get out of this course. So if you see a machine learning model like that, maybe think again, right? And that's a good thing to do today, because we will see some, let's say, unreasonable numbers spent on energy for training these models so that machine learning models can become slightly better. So how do we make that fundamentally efficient? Well, that's a systems problem, basically. It's all the way from algorithms to devices that we design. We need to make everything efficient. Because if you don't, maybe we'll not have this world in 20 years or 30 years. Some people suggest 2050 or so, but you never know, right? Anyway, I digress. This lecture is about digression also currently, but okay, so I do research and teaching in computer architecture, computer systems, hardware security, bioinformatics, and you'll see a lot of it clearly in this course. We'll start from the beginning, of course. And these are some research topics that we look at. I'm not going to go through everything over here, but clearly I find it exciting. That's why I do research on these topics. And we'll sprinkle some of the ideas that we work on also, that people are working on in general, into this general course as we go along. Of course, we will start with baby steps, right? You're not going to be exposed to some big complicated system right away, except for this lecture. In this lecture, I'm going to give you some examples of complicated systems that we're designing today, just to motivate you, so that and to show you that there are some big systems that are being designed today. There are some small systems that are being designed today, and that's for a purpose, basically. But maybe we should be rethinking how we design the systems today also. And again, that's what we have been doing in our research. But down the road, that may be something you will have to do also. In fact, I will argue that you will have to do it much, much more than I had to do it, because your generation is going to be faced with much worse problems, unfortunately, I will say, because of perhaps the bad decisions that were made over decades and decades. And we're going to have a huge problem with climate, pollution, etc. So I hope some of you will be there to solve it. Sorry, I didn't want to be that negative to begin with, but I think I think there's some reality. You need to be realistic how you look into the future, right? Future is at some level very bright, but at some level not so bright. The question is, how do you actually make sure that the bright things overcome the not so bright things? Okay, well, that's another picture of me. That's one of the brighter days, let's say. It's in a good place in Zurich. Can anybody guess where this is? No, this is Zurich. Close enough. That's the closest guess I have received so far. Say it again. Where is that? Okay, I think you're right. Okay. It's close to the Chinese consulate. Okay, absolutely. You got it. We should give him a bonus point. Okay. Okay, so let me tell you a little bit about myself and the group who will be teaching this course. We work on research, as I said, and my goal is really to build fundamentally better architectures. As I said, we want to make the architectures fundamentally better than what they are today. And architectures consist of everything that you see here and more. Basically, how do you make the chips fundamentally more efficient, fundamentally higher performance, fundamentally secure, safe, reliable, which is this slide essentially. We will talk about this briefly in this course also. And how do you make these chips or systems overall? You will see that it's not just about the chips, basically. This thing, for example, this cell phone is not about just one chip, right? There are tens of chips in here. It's a system on a chip. Some of them are extremely specialized. Some of them are very general purpose. And they all work together, basically, to do things. And this is not the most sophisticated system in the world. There are more sophisticated systems, but this is actually a pretty good system. One of the fastest and more efficient systems. So it's all about systems we build today. This is also a system, basically. It's not just about one chip in the end. It includes, the system includes a software model, programming, etc., because that affects a lot of things as well, because energy is spent on the software as well. So basically, these are some of the current directions that we're following. We're going to talk about some of these in this lecture. So architecture is specialized for different processing, like machine learning today, important. Genomics, medicine, and health. That's also important to me, basically. And how do you make systems lower latency and much more predictable is also very important. These two things are different, by the way. Lower latency is very different from predictable. Do you guys realize the difference? Low latency means you get the answer quickly, right? Predictable means I don't care about how quickly it is. I care about how I can predict it. For example, I like the example of train schedules or plane schedule. Let's take the tram schedule in Zurich. Right? The tram, I don't really care about how quickly it comes. I care about whether that tram comes at the time I arrive at the station. If it comes too quickly, I miss the tram. I don't care about that. I care about whether it's there at a predictable point. So if the tram is scheduled to be at a station at, I don't know, 14:40, 8 minutes from now, if I go there at 14:39, I expect that tram to be there or to not have left the station at that point in time. That's predictability. If the tram actually left at 14:38, even though it was scheduled at 14:40, it's low latency. But it's useless for me. In fact, it screws up all my schedule. So you may have low latency, but you may not have predictability in a system. And that's key, actually. In fact, this happened to me many times. I go there, stand over there, wait, assuming that the tram didn't leave, actually. In fact, the tram has left 1 minute before. But it was not supposed to leave at that time. Okay, anyway, that's basically, hopefully this is an example of predictability and low latency. So it's important. One of the things in this course that's important is understanding the concepts fundamentally. Sometimes people actually confuse low latency and predictability. Yes, is there a question?
Yeah, why must high throughput? Why is that a concern?
Yeah, high throughput, certainly. It's also a concern. How quick, how many things you can generate, how many data elements you can operate on, for example. Yes, that's a concern, but that's kind of implicit, I would say, in here, and maybe the last bullet over there. And also, there's another answer to that. A lot of people are working on that topic. How do you make things high throughput? These are some of the topics that, let's say, fewer people are working on, and we believe we can make a bigger difference in those areas. Very good question. So high throughput is also different from latency, right? Latency is how quickly you can get one element, or how quickly you can do one thing. Whereas high throughput is how many things you can do in a given time. Okay, we'll talk about that later. Okay, so I don't want to go into a lot of detail on research, but data is a big problem, and we will get to it toward the end of this lecture if we have time. And our goal is really to design fundamentally better systems and architectures. And I believe they need to deal with data well. They need to be data-centric, meaning do not move the data a lot around. We have a lot of data today. We can generate a lot more data than we can process. How do you actually be frugal about it? The machine learning example that I gave you earlier, it takes so much data to really understand what's going on. And even then, understand is in quotation marks, right? Is it really understanding things about data, or is it really, I don't know, some statistical model, basically? But can we actually be much more data-centric? Can we be more data-driven and data-aware? Don't worry about these details right now. But let me introduce my group also. Several of them are here in the front. They helped me set up. But you can see that we are a big group. We have more than 40 researchers. You can see 3 of them. I will name them. Mohammed here is one of the major TAs. Ataberk here is a new PhD student. And Mohammed is a postdoc who's been with me for some time. And John is a PhD student also. So they're going to be your TAs, in addition to some other people. And if you want to learn more about us, you can read. You can see pictures here, for example. And you can also read some of the newsletters if you're so inclined. Maybe it does for a good bedtime reading. You know, depends on what your choice is. So we have a lot of alumni also, and I'm proud of them. So let me talk about the course also. Clearly, you're here for the first course, but we also have a seminar course that you can take. In fact, people who are excited about computer architecture usually go ahead and take that course. And if they're also really excited about architecture, they can take the advanced computer architecture course, which is a master's level course. And you can find all of them online. In fact, this is the last incarnation of digital design and computer architecture. Unfortunately, it is fully online, but you can also watch those lectures instead of coming here. But it's good that you guys are here. I'm not discouraging you not to come. But we're going to essentially follow very similar material, not significant changes. Of course, I always update the course with some things that I believe are important to change depending on the situation. So you will see some examples in this set of slides also. So this is the computer architecture course. Again, everything is online. You can study them. This is a seminar. And we also have hands-on project courses. You can find a processing in memory course, for example, genomics courses, and heterogeneous systems course. So I'll go. This is just to give you an overview of what we do, basically. So we also have live seminars. And in fact, I would like to invite you to one of them that's going to happen next week. This is February 28th, next Monday, 6 p.m. Zurich time. This is going to be about, Sean Lee is going to give a talk, as you can see the title, Thinking Outside the Die, Architecting the Machine Learning Accelerator of the Future. And he is the co-founder and chief architect of this very interesting company, Cerebras, which builds wafer scale chips. Chips are this big, basically. You can hold it like this. And I'm going to show you pictures of this later in the course. And the reason is, again, machine learning is extremely computationally and memory intensive. If you really want to do a good job in machine learning inference and training, you need to build a chip like this, according to them. And I actually like their direction, and I invited them to give a talk. And I would like to invite you to this. We're going to share the Zoom link, so you can join on Zoom. You don't have to join on YouTube, but you can also join on YouTube if you're interested. You can also ask any questions you may have. Okay, so let me give you my mindset before we go into a little bit more interesting stuff, let's say. Maybe this is interesting, we'll see. So I like principles in general, and I think in the next few lectures, we're going to talk about some principles, and I will point you out some computer architecture and systems principles as we go along. But I'd like to give you some basic principles that we follow in our research. First of all, I think teaching is very important for me. Education and research, these go hand in hand. It's not just about research. It's not just about education. These have to go hand in hand if you really want to advance the society. You have to do cutting edge research so that you can leap forward, right? If you actually say, oh, I'm happy with what I have, I'm not going to do anything, then that's the end of progress, right? You have to do cutting edge research to leap forward, but you have to educate also to leap forward. So if you just do research without education, that's not leaping forward, because there will be a huge disparity in the society. But if you do research and teaching, and if you keep doing this, then you actually have a much higher impact on progress. So that's why we actually incorporate a lot of research into the courses. You will see a lot of cutting edge activities that are happening in this course, in this particular lecture also in a little bit. I like insight a lot. I think hopefully I'll try to point out the insight of the ideas to you. There are a lot of details. So everything in the world can be explained with fundamental insight and the details, right? The first thing that's really important is, what is the fundamental insight? And I'd like to give you that in the ideas that we cover in this course. Details we will also look at in some cases, but you cannot just focus on details, right? You will, for example, build a processor in your labs here, in the FPGA labs. There you will go into the details. But the courses, the lectures will be mainly about giving you the insight of the idea. Like, what is the main contribution to the advancement of knowledge? And I encourage new ideas also. If you have new ideas, if you think some way of doing things is not good and you have a better way, please talk to me. I think that's really important in a university setting. And again, in my opinion, anyone can do this. Like, advancement is really inclusive. It's not like you have to have a huge degree to make a huge advance in something. You just need to think differently and critically and understand something and develop new insights. None of them talk about a degree or anything. This is really all about your thinking process and mindset. It's really all here, in my opinion, and also how you process what comes from the outside in here. So some people who have taken this course later did research with us, for example, and they came up with good ideas. Some of them are published, and they're advancing the field right now. I'm going to point out one of the papers later on. The SIMDRAM paper in Asplus, for example, was sparked by a bachelor student who was in digital design and computer architecture, who later took our seminar course and then did research with us for his thesis. Okay, I like focusing on learning and scholarship, and I advise everyone to do so also. I mean, they're clearly, universities should be a place for this. Not always they are, but they should be. I think learning and scholarship is really critical. So if you approach everything, what can I learn from this? So you go and attend a talk, let's say, it looks terrible. You can still learn something from it, right? So that's a good approach. That's a good mindset from my perspective. Don't think that you're not learning from something. Even from bad examples, you can learn, in my opinion. Okay, I should go through this relatively quickly maybe, but this is what I like also in research as well as teaching. I think it should be all about critical thinking, free exploration, critical exploration, openness, collaboration. In the end, you have to put in the hard work and creativity. That's what we do in our research, for example. I'll give you some examples of it, maybe today, maybe sprinkled toward this course, in the rest of the course. And I think I strongly believe in this also, right? How quality, what kind, the quality that you put into your work defines your impact in the world. And it's not just, again, in my opinion, these are principles that we employ in research and education, but I think these are more general principles. If you want to be successful in life, for example, whatever you do, I don't know, build a company, you need to put in some quality. And I think in the end, your quality defines your impact. Okay, we can go into a lot of case studies over here, but we don't have time. And I believe everybody, and I'm especially hopeful for you over here, with good mindset, good goals, and good focus, you can make a good impact on the world. Some other things that we follow, following your passion is important, I think. For example, I don't know, you may want to reduce carbon emissions by 50% in 5 years, right? That sounds like a good goal. Unfortunately, not many governments have that goal, but I think people should probably have that goal. Maybe you should work toward that goal, right? That's a good passion to have. There will be naysayers. Many people will, for whatever reason, it could be, well, you can think of reasons, right? It could be they don't believe it. It could be they have some ulterior motive. They will not benefit from what you do. They will try to derail you. But if you have a good goal, follow your passion. And I think building infrastructure, this is specific to research perhaps, but you need to work hard basically in the end to enable your passion. You need to build something. You need to show that your idea works, right? And this lecture is all, this course is all about showing ideas that work. And some ideas that don't work and why they don't work, or under what conditions they don't work. We're going to examine a lot of these trade-offs basically in this lecture. And I think I already said this. So in the end, I think people who change the world are resilient and focused. They don't get distracted or detracted, and they make things happen basically. Hopefully, I'll give you that mindset in this course also, but because I think this is a really important mindset, right? Making it happen. There's no other way, in my opinion, to make progress. And again, I will finish with this one. Maybe I've given you a lot of these slides, but I believe everyone can make a good impact on the world. Okay, I mean, there's a lot of material that we talk about in research. I'm going to refer you to these talks if you're interested. Some of these talks at some point will be assigned as extra credit. We'll also talk about that. But you can find a lot more information, basically. I think if you want to have more of this kind of discussion, you can watch some of the talks that we have delivered on some interviews. Okay. Any questions? Okay. Okay, so let me talk about how to approach this course. I think maybe this gives you an idea. This was the mindset part. Why? I don't like this. You know why? Because there's a... I've been doing that a lot recently. I don't know why. Yes, please. Okay, that's a great question. Basically, the question is, I'm repeating for people online because they cannot hear you, I think. I studied computer engineering and psychology. Did I find any connection between the two? Yeah, absolutely, yes. I think there's a huge connection, especially in cognitive psychology, artificial intelligence. But that was not the reason why I studied psychology. But I like that connection for sure. And I think we need to look more into these connections across the field going into the future. Does that answer your question? More can be talked about this, of course, right? Because, I mean, psychology is also very broad, right? But there's a portion of psychology that is neuropsychology that studies brains and how people behave. And basically, the cognition, how that works, consciousness. Of course, we don't know a lot about consciousness, but we know some of the mechanisms underneath. And there is a lot of relationship between artificial intelligence, better machines, things like that. Okay. Okay, let me talk about how to approach this course. By the way, it's good that we're having this lecture in person because in my experience, there are not such questions that are coming in Zoom. Unfortunately, you don't get this sort of interaction in Zoom So if you're attending the class here, if you want to ask questions, probably it's best to attend over here. So how to approach this course? I think I'm going to give you some, at least people who have enjoyed the course have made some good comments. And I'm going to give you, I believe they have a mindset that's a bit different. These are some of the comments that we received. They think it's a formative experience. Hopefully you will look at it that way also, as opposed to just something where you will get grades. You can also do that, and that's your goal in the end, right? But maybe you may not enjoy it that much if your goal is to just pass the exam and get a grade, which I believe is not that hard, frankly. In the end, I mean, in the end, if you look at, everything about the course is online. You can go back last few years and you can look at the exams. You can look at what kind of questions come up. It's more or less similar, right? Yes, there are some differences over time, but yeah, if you study for the exam, you will pass this course. But hopefully you will take it to a level that's better than that, right? High investment, high return. I'm not sure if high investment in the sense that if you really want to do the job, let's say. If you really want to take a lot out of the course, I believe this is high investment. You get high return in the end as well. I agree with that. But if you just want to pass the course, I think probably you can. If you're smart in terms of how you handle the exam, then I think you can do it without that investment also, frankly. I'll let you think about what that means. you focus on the right parts of the course, right? For example, homeworks, I would definitely ask people to do the homeworks because that's good for understanding, but that's also good for your study for the exam. Even though they're called optional, because we cannot have more than a fraction of the grade option coming from assignments in a bachelor's second semester course. Optional means you don't get a grade by doing the homework. You just prepare yourself better for the future, especially the exam, let's say. Okay, record lectures. We're recording everything, so hopefully this is obvious and hopefully this will be useful. We've been doing that for almost a decade now, actually. And I guess you can you can do that also. You don't have to sit here on the maybe uncomfortable chairs. You can sit on your sofa and drink your beer and yeah. Okay. Yeah, I will try to be. As I said, if you actually have questions, remarks, I'm very open to answering them. We have some material to cover. If I cannot answer that, I will tell you, okay, we need to finish the material, but usually we have some flexibility. So feel free to just ask questions, whether during the lecture or outside of the lecture, outside meaning in the breaks or over email, etc. But email, don't forget my comments. Yeah, I don't know about this. Some people like the online experience. How many people prefer to be purely online? Okay, I see 0 hands, I think. How many people prefer to be in person in class? Okay. How many people don't care? Okay. I think those are the full choices. Maybe we have a selection bias here because clearly you're all here. Okay, well, hopefully every one of you will feel this way, but I have a feeling that not all of you will feel this way. Frankly, there are very few courses that I would do anytime that I have taken in the past. There are some. Okay, so I think I would suggest that you approach this course as a learning experience as opposed to just passing an exam experience. Think about long-term trade-off analysis, like the critical thinking and decision-making skills this course brings to the table. And I will try to emphasize that. We'll cover a lot of ideas within the domain of computer architecture and digital design, sure. But a lot of the analysis that we make, analysis skills, critical thinking skills, trade-offs, maybe we should think about it this way or that way, that is much more common than, that's basically about life in the end. In life, you make these decisions. And I think this sort of trade-off analysis done on many, many ideas can enable you to think in a different way. And we'll cover a lot of concepts and ideas, as I said, this way. We'll cover a lot of fundamentals as well as cutting edge. And hopefully you'll have a lot of hands-on learning through the labs. And in the end, I think like everything else, your mindset will determine what you get out of the course. And think about it that way. If your goal is to pass the exam, then have that mindset. I wouldn't recommend it for, let's say, the bigger educational goals that you may want to reach, but that's your mindset. In the end, it's your life, right? It's your decision. I cannot make that decision for you. If your mindset is you actually want to do something bigger, then you can get something bigger perhaps. And in the end, I would recommend find and choose the learning style that works best for you, because we have a lot of flexibility. Again, you don't have to be here if you don't like it, for example. We have a lot of course components, lectures, readings, labs, homeworks, exam, and extra credit assignments. And in all of them, you have the freedom to adapt them to your learning style, right? Lectures, we have many different ways of attending lectures, for example. You don't have to attend also, as long as you learn the material. There's no attendance that we take, that I take. I don't believe in it. I think it's important for people to decide what they, and every one of you here, I think, are bright minds. You can decide on your own how you actually approach the course, right? Readings, labs, homeworks. I think homeworks, as I said, it's important. It's going to be important. And we'll have extra credit assignments, so they could be a good way to learn more as well as boost your grade. Okay, we'll talk more about these later, and you know the course website, so you can actually find a lot more about these online. Okay, that brings me to, let's say, the real material. Any questions? Okay, so let's jump into what will we learn in this course. And I think my simple answer is how computers work. And we do it from the ground up, meaning from the transistor level. And of course, why we care, hopefully. You may, probably people have ideas of why is it important to learn how computers work. Some people may not care, but I believe it's really important to know how computers work so that we can solve some fundamental problems into the future. But before we go into that, why do we have computers? Anybody? Wouldn't life be better if we didn't have computers by now? Some people are saying yes. I don't know. Say it again. Say it again. Interact with human beings. That's one specific case, I will say. Anybody else? Yes? We're lazy? Okay, maybe. I don't know. To compute things, okay, but why? Yes. Okay, yeah, that's one. I think you're giving me some points that all make sense, no question about that. But in the end, I think, well, I guess this is the other way of thinking about question, why do we do computing? I think the very general answer is we have a lot of problems and we want to solve them, right? You can, even if you don't think about this a little bit, even if you don't think something doesn't look like a problem, even if you think something doesn't look like a problem, you can express everything as a problem, right? For example, communicating with people, right? We have a problem, we get better methods of communication using computers, potentially. So this is the overall general answer I would give. If you reword this, I think we want to gain insight in some way. And this is the answer Richard Hamming gave. How many people know about Richard Hamming? Hamming codes. Okay, good. I see a lot of hands. Not so many hands here, but we may talk about him later on. But he's the inventor of Hamming codes, and he is a winner of the Turing Award. And this is what he said. Computers are there to gain insight. Crunching numbers is good, but in the end, you want to gain insight out of those crunching numbers. My example of a machine learning model requiring millions of cat pictures. It's crunching numbers. It's training a model. It's doing a lot of multiply and accumulate operations. Is that to gain some insight? What is the insight? Next time you see a cat, you would like to be able to recognize it. Right? That's the idea. And I think maybe if you extend it, you want to enable a better life and future going into the forward, right? Why do you want to? We want some benefit out of this in the end, right? Okay. So then the question is, how does a computer solve problems? And this is where we get a bit more technical. And my answer, well, maybe I should have asked you, but I think I've given you an answer. Today's computers at least orchestrate electrons to solve problems. Right? That's how this machine works. That's how all of these machines over here work in today's dominant technologies. That's what they do. How many people have taken a physics course? Hopefully in your high school. How many people, okay, everybody's raising hands in high school. Probably not here, yes. How many people liked it? Okay, I see really firm hands. How many people disliked it? Okay, I'm sure there will be firm hands here also. Okay, that was just a question. So the question is, how do problem gets solved by electrons? And that brings us to the computing hierarchy. They call this a transformation hierarchy, or the computing stack, let's say. Some people go, I like the transformation hierarchy better. Your problems at the top, You have electrons and physics principles of electrons at the bottom. Now, it would be nice if I knew the electron language. As a human, I go to the electron, go and solve this problem for me, and coordinate. That's how I coordinate. But that doesn't work. I don't have a language to communicate with electrons. I have an interface problem. Electron is an interface problem. We cannot communicate. So we built a hierarchy. Problem gets transformed into an algorithm. Algorithm gets written in a programming language. It gets executed in an operating system, which consists of many, many components. And the program gets compiled down into a software hardware interface instructions that are communicated to the computer. Computer has a microarchitecture that can execute those instructions one by one, and we will see a lot of that. That microarchitecture is implemented on logic gates, which are built on transistors, and transistors operate based on electron principles or electrical principles, let's say. And that's the transformation hierarchy, basically. That's how we can communicate with electrons so that we can get electrons to do what we want them to do, to solve our problem at the end. And your problem can be anything, right? It can be, maybe your problem may be frivolous to someone else, right? In the end, you can express any problem this way. So computer architecture, the narrow view of computer architectures, it's the software hardware interface and the microarchitecture. That's a very narrow view. In fact, if you take this course, probably in most universities in the world, you will get that narrow view. I believe it's much bigger than that. It's actually algorithm to devices. Yes, the core is at that orange part over there, but the bigger part of computer architecture is really spanning across the stack. How do you take an algorithm and implement on a machine and also design the machine to actually execute that algorithm? We will talk about, for example, machine learning accelerators that are built by many, many companies, Google, Amazon, Tesla, whom you may think is a car company, but it's not a car company. It's really a technology company. It's more than a car company, basically. Cars, perhaps, is a interesting effect that comes out of what they do. Okay, so this is the expanded view, basically. And I'm going to subscribe to this expanded view. And this is Richard Hamming, who said the purpose of computing is to gain insight. And we gain and generate insight by solving problems. How do we ensure problems are solved by electrons, basically? That's the question. Right? And again, solving problems, self-driving car is a problem, right? How do you build a self-driving car? It's really the full hierarchy. And then you need to design the system. System becomes extremely important also. Okay, I will go through this slide very quickly. You covered algorithms probably, right? You've taken an algorithms course? Okay, so I'm not going to cover this. This is for your benefit. I mean, you need to know what these are. Algorithm, I'm not going to test you on it. But algorithm is a step-by-step procedure that is guaranteed to terminate, where each step is precisely defined and can be carried out by a computer. So it has three properties: finiteness, definiteness, effective computability. If you had more time, I would tell you more about algorithms. But there could be many algorithms for the same problem. Clearly, there could be many programming languages, many operating systems, many instruction set architectures, as we will see. That's the interface or the contract between the hardware and the software. What the programmer assumes hardware will satisfy. We'll talk about that in lecture 9, for example, especially. And microarchitecture will cover a lot between lecture 9 to the end of the course. That's the implementation of an ISA. And we'll see many models. So let's go for some time as we started late. And then logic gates. We'll actually cover the logic gates earlier in this course. These are digital logic circuits, building blocks of the microarchitecture, and devices. So in this course, we're not going to cover the devices except for the transistor. We're going to talk about transistors, operation modes, and what we will assume. And then we're going to build up. You don't need to know about electrons. So for those people who have hated physics, don't worry. It's not about physics. In fact, if you really want to learn about how a transistor works, there's a lot of exciting stuff that's going on in microelectronics today also, but we won't have time, and it's not the subject of this course. So this is the focus of the course, actually. Logic, microarchitecture, ISA, but I will actually broaden it to the software aspects and how the software can utilize the systems much better. So that brings me to the definition of computer architecture, right? Hopefully you wanted a definition in this first class, and this is my definition. As you can see, it's broad. It's the science and art of designing computing platforms, basically. And that is vague in the sense that it actually encompasses a lot of things. It's the hardware, it's the interface, it's the system software, it's the programming model. And today, we're designing full computing platforms, as we will see in the remaining part of the lecture. But why, when you're designing the platform, you have a goal, right? You have some design goals. And we'll take a look at some example platforms. Design goals can be actually very sophisticated, but one could be this. I want the highest performance on Earth on workload X. Ignore the Y and Z. You can more generalize it with Y and Z. These are the workloads that I care about, and I want the highest performance. That's it. This is the example of a supercomputer, right? Is there a question over here? Okay, maybe I'll handle that later on. How do I get rid of this? Okay. Okay. Or you want to get the longest battery life at a form factor that fits in your pocket with cost less than some Swiss francs. This is a different design goal. It may look like this in the end, the system that you design. Or you want to get the best average performance across all known workloads at the best performance per cost ratio. This is a more general purpose system. And many, many, many other things. You may want to just a specialized task, right? You want to be able to communicate with some other human, and that's it. That's all what you want to do in any language. Okay, in one language, let's make it simple. That's a computer, right? You need to design a platform for that. So in the end, designing a supercomputer is different from designing a smartphone, no question about that, but many fundamental principles are actually similar. And hopefully in this course, you'll get exposed to many of those fundamental principles. Now let's take a look at some pictures. Again, as I said, relax. This lecture is not going to be hard. You probably know all of these. You probably have seen things like this. These are different platforms. They have different goals, right? And they have different constraints also. This thing has a much higher battery constraint than my cell phone or something else over here. And maybe a security constraint also. There's another platform. How many of you have this? How many of you have watched this? Mr. Bean. Okay, you watched Mr. Bean, so that's good. You know how a self-driving car can be built now. Of course, that's a joke, but that's an example of a self-driving car, right? And ideally, we would like to be able to trust your self-driving car without touching it, but we're way far from that. And these are some examples of self-driving cars. You can see computing platform is a big part of it. This is a data center, a totally different goal here, right? It takes programs from many people and executes them. Or it takes your Gmail or whatever mail you're using and enables you to have access to that sort of mail service. There could be many, many even data center platforms can be specialized for different applications, right, in the end. This is a supercomputer. It may look similar, but it has a totally different purpose. Its purpose is to execute some important high performance computing, scientific applications in the highest performance manner. More recently, they've also been taking into account energy efficiency, not just performance. This is from China, Tianhe 2. It was at some point the fastest supercomputer of the world. But if you care about what is the fastest supercomputer of the world today, this is Fugaku from Japan. So it's clearly much more efficient today. In fact, it has more than petabytes level of storage. You can read more about these clearly, but clearly there's a race to build supercomputers also. This is another platform. It's a board that can execute machine learning tasks, machine learning inference, built by Google in 2016 or so. It's a specialized accelerator. The goal is to execute machine learning models fast so that you can recognize a cat. Of course, that's one example, right? It can do many other things. It can do translation from one language to another. Why? Why did they decide to do that? Because it was not enough to use general purpose computers to do that task in their data centers. They said, we want to build our own computers. You don't think of Google as a hardware company, but it's a systems company. Systems includes hardware. And this is actually really important for them. This is the version 4 of their platform, much more capable. It was introduced last year. This is Tesla. It's their board. I think they call it the self-driving computer. Maybe this is an earlier generation. And their goal, again, is to design a self-driving car that can quickly make decisions, right? Quickly detect a pedestrian, for example, detect something that's blocking the road so that they can make a decision. Why didn't they use general purpose chips designed by Intel and AMD? Because they know their software and they want to do better. Those chips were not enough. We have these demanding applications that require building systems like this so that you can make intelligent decisions much faster. Of course, you can always argue that this is not intelligent enough yet, and I absolutely agree. But there's a reason why people are building these systems, platforms today. This is more recent, Tesla's, they call it the Dojo chip, I guess, or Dojo system, D1 chip. And the goal here is to learn the model so that these chips can execute them in the field. The machine learning training is done on these chips. And these chips are actually a much bigger part of a data center, as we will see. They introduced this last year. And you can see this little data center. I didn't have a better picture over here, but this data center consists of many, many of those D1 chips so that they can train big models. You can imagine how, and their goal is to really collect all the data that they have worldwide and train a model so that they can make more accurate decisions in the field with these chips connected to the cars. Does that make sense? And you can see, I mean, this is a funny picture. I'll show you another example picture over here, but this basically shows the computing requirements by neural network models. As your neural network becomes larger, your computing requirements becomes larger like this. And this is a picture from their, in fact, I would recommend you to actually look at their YouTube video. They call it the AI Day, I think, Tesla AI Day. You can find easily. They have a beautiful 3-hour YouTube video that talks about different components of it. And they basically talk about what I talked about, right? The transformation hierarchy. It's all about the transformation hierarchy. It's chip, you build a chip, you build a system, you build a cluster, and you build the software on top of it. Software includes, of course, algorithms, languages, compilers, system software, everything over there. This is my transformation hierarchy, kind of dumbified by Tesla, let's say. But it's real. This is another chip. This is the wafer scale chip that I was talking about. The goal is, again, to do machine learning training and inference much faster. And these folks said that, oh, existing GPUs are not enough. We need a lot more computation power so that we can train machine learning models. So we're going to, normally what you do is you have wafers that are circular like this, and you cut chips out of those wafers. So a wafer basically gives you, I don't know, 60, 100 chips. And that's the GPU, one of those chips. These folks said, we want a much bigger chip, so we're not going to cut the wafer. Well, we're going to cut it just to be rectangular so that we can put stuff regularly in it. And this is our chip. And this is the chip that you will learn about if you attend the lecture on February 28th. These are some other computing platforms. These are genome sequence analysis platforms. You can sequence your own genome, for example, with the right, let's say, preparation. And then you can connect it to your phone, and you can maybe make sense out of your genes. I think this is fascinating also. You can see this is a completely different platform. It's specialized again. And we'll talk about that also maybe as time goes. This is another thing that was recently introduced in 2021. This is a processing in memory system. We will see that existing machines have processors, memory, they're far away from each other, and they communicate. As a result, a lot of data moves between them. This is extremely inefficient. These folks from UpMem said, why don't we have memory and put the processor inside so that data doesn't move out of the memory? And data movement is extremely expensive today. So you may think, okay, computers are good number crunchers, right? They're actually extremely good number crunchers. A sophisticated addition operation consumes, let's assume that it consumes 1 energy unit. A data movement operation consumes almost 3 orders of magnitude more, basically 1,000 energy units. So data movement is much more expensive than computation today. That's why people are trying to build systems that look like this. Okay, so basically, why am I telling you all this? These are all systems, and these are all system designs. They're not just hardware. They're really the expand view of computer architecture. You have some algorithm software, and you want to run them efficiently. Well, you cannot run them efficiently with the traditional thinking. You really need to design your system from the ground up so that you can run machine learning efficiently. You can run some data analytics efficiently. You can run your database efficiently. So that's what we're doing today, basically. We have this expanded view of computer architecture so that we can maximize energy efficiency and performance. And we need to co-design across the hierarchy, algorithms to devices, and specialize the system as much as possible to attain our goals. Of course, this all depends on your goal in the end. So I think I've already defined computer architecture, but this is another definition: the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, and other specific goals. Let's talk about why study computer architecture. We want to enable better systems, clearly. We want to make computers faster, cheaper, smaller, more reliable, more energy efficient, clearly. Didn't I say that over here? Amazing. We want to exploit advances and change in underlying technology and circuits. We want to enable new applications so that we can solve our problems better. And today, we're much better at that because thanks to the computing devices that we designed, like visualization, self-driving cars, personalized genomics. In fact, machine learning is really due to computer architecture also because of GPUs. So if you look at the training algorithms or neural networks, they were designed in the 1980s. Unfortunately, because of the data requirements and the training requirements, computation requirements, they were not really successful until 2012 or so. In 2012 or so, some folks, some actually graduates and undergraduate students from University of Toronto figured out how to use GPUs to train these models very fast, extremely fast. And after that point, this was called ImageNet. Actually, they did very well in that competition. And after that, machine learning took off, basically. The GPU, graphics processing unit, was so powerful because of its design that it enabled the new machine learning revolution that we're experiencing today. So you see that these systems can enable new applications. Yes, please.
Do we still use GPUs as the main processing deployment for machine learning, or have we basically taken the person that the GPU also deal and making it to special rules?
That's a great question. Basically, the question was, do we still use GPUs for machine learning, or do we take the best parts and have a specialized machine learning accelerator? I would argue that we do both. So if you really want to get high efficiency, you need to specialize much more than a GPU. Even GPUs actually have specialized parts today called tensor cores by NVIDIA, for example, that are specialized for machine learning. But many people in the world still use GPUs. I would argue that they're not cutting edge. The really cutting edge people are actually those who are designing their own accelerators, incorporating principles and ideas from GPUs as well as other things. That's an excellent question, and we will see some of those later in the course. We'll talk actually in this lecture. I will hopefully get to some of them as well. Okay, so we would like to clearly new applications can be enabled. Enabling better solutions to old problems is also possible. It's because software innovation is actually built on trends and changes in computer architecture. For decades, we've had more than 50% performance improvement per year in hardware. It's getting much more difficult today, but with specialization, like we've been talking about, you can enable better solutions. And I think the last thing that's important also is understand why computers work the way they do. Like, why is it important? Well, I guess the boring answer is you're here for a computer science degree. You'd better know how this thing works, right? I don't like the idea of like being a computer scientist without knowing how really the system works, right? Yes, you may say, okay, I stop at Python, and Python is the lowest level of abstraction that I have. But then you don't know how Python gets executed in a system, right? Everybody can do Python. In fact, probably you learned Python in your high school. Right? How many people learned Python in high school? There you go. Yeah. If you want to be a software engineer, you don't need to know any of this, perhaps. But if you want to be a good software engineer, I think it's important to know. So let me cover these slides and we'll take a short break before we move on. So I think today is a very exciting time to study computer architecture, actually. Industry is in a large paradigm shift to novel architectures, and many different potential system designs are possible. I'm not going to go over all of this in this lecture, but there are many difficult problems motivating the shift and caused by the shift. You can see some of these over here. But there are no clear definitive answers to these problems. We're going to see some of the problems in the later part of the lecture. That's why I'm going to skip these over here right now. And computing landscape is actually very different from 10 to 20 years ago. Applications and technology both demand new architectures. So if you look at these components that I showed you earlier, everything is being re-examined. People are not taking, at least the cutting edge people, right? If you're at the cutting edge of technology, you have a very different view for technology. If you are not doing cutting edge things, for example, if you're not pushing the boundary of self-driving cars, there are some problems you don't even see. If you're pushing the boundaries of self-driving cars, there are problems that you see no one else sees, let's say. That's an example of cutting edge, right? If you're pushing the boundaries of robotics, there are some problems that no one else that you see that no one else sees. So at the cutting edge, people are re-examining everything. But of course, let's say the general masses who are not at the cutting edge are still using CPUs, GPUs, etc. But they're not at the cutting edge. They're not the people who move and change the world, let's say. Okay, so this is my axiom. Maybe I'll quickly also talk about this. So basically, how many people know about Richard Feynman? a famous physicist. Okay, good. People who like the physics lecture probably know about Richard Feynman. So he was a famous American physicist, Nobel Prize winner also. But basically, he's known for saying this: there's plenty of room at the bottom. So think about the transformation arcs that I showed you. Problems, electrons. At the bottom, there are electrons and devices, right? There's a lot of room there, basically. We can grow. We can enable computing to be much better by doing innovation at that level. And that's actually very interesting, right? Nanotechnology has happened this way. Today, a transistor is very small, on the order of nanometers. Even less, actually, people are pushing that. There's a lot of interesting technology at the bottom, let's say. And that's going to be even more important in the future because we're having limits, we're having difficulties in reducing the size of the transistors today, for example. But if you imagine, if you're a person who wants to push the boundaries, maybe you should really think about direct manipulation of individual atoms so that you can enable new forms of synthetic chemistry, etc. And there are other examples like denser computing circuitry. What can that enable? This is based on a talk that he delivered in 1959. This is the title of the talk. But if you think what you can do at the bottom, you can actually enable a lot of interesting things. Like he mentioned swallowing the doctor. Essentially, you swallow something that figures out what happens in your body, right? And gives you a recipe of how to get better. Okay, so this is the bottom of this computing stack. I believe that there's a lot of opportunity over there. So don't dismiss what happens at the bottom. Always look forward to the technology and maybe enable it. But there's also the top of the computing stack, which is software, algorithms, and architecture is actually closer to the top, more closer to the top than you think, especially if you're working at the bottom. So basically, these folks say that it's becoming difficult to improve performance by reducing the size of the transistor. So we should focus a lot on software and higher level algorithms. And I agree with this. I agree with both points of view, actually. But I will revise it a little bit. I think we have both plenty of room, both at the top of the computing stack, software, as well as bottom, electrons and devices. But you can do much more so if you communicate well between and optimize across the top and the bottom. And that's the software hardware co-design. And that's what these folks who are pushing the boundaries are actually doing today. And I think we will see much more of this, much more novel systems. I think quantum computing is one example also. It's a bit farther out, but it's one example right now. There's a lot of development at the bottom, and people need to develop algorithms at the top to actually match what's going on at the bottom. Okay, so this is a great place to take a, let's say, 10-minute break. Okay. So let's talk a little bit more about cutting edge in computer architecture. Yeah, keep the questions coming. I got a lot of questions during the break. That's great. Now we will go into a little bit more things. Why is computer architecture so exciting today? I thought I already talked about it. But I think there's even more interesting things happening in computer architecture today. So there are a lot of problems that we need to solve. Performance and efficiency. I should add sustainability over here also, but I think efficiency is about sustainability. And the question is, do we want a world that looks like this going into the future, or do we want a world that looks like this? How many people choose this one? Okay, good. How many people choose this one? Okay, there are people who choose this one. Okay. Maybe we should ship you back to 1940s, 1900s to Pittsburgh. You may like it. But I think I would argue that we want efficiency and sustainability, but we don't want to give up high performance. Because high performance is needed for us to actually solve the problems, but we want to do it in a very efficient and sustainable manner. And I think this is a huge challenge going into the future, and future is today. We have to do it today. If we're late, we may be too late, basically. Because we have many difficult problems. Climate is one of them. Hopefully you are familiar with it. We're having a lot of issues here. Intelligence is another one. How do we understand intelligence and also maybe build more intelligent systems going into the future? Hopefully, if we cannot save ourselves, maybe they will save us, right? Who knows? But as I said, there are a lot of issues here, right? I wanted to actually put these over here because it's not just about putting performance and performance and performance and performance at all costs. Unfortunately, we have a lot of issues with the way we're approaching intelligence today. So probably some of you will take machine learning, artificial intelligence courses, and you will see the sophistication of the models that are out there. But it's not about pushing the model to have more parameters like we discussed with recognizing cats, for example, right? Because that is extremely energy inefficient to train. And if you're interested, you can read some of these articles. There are many, many articles that are written on this topic more recently. But we need to be a little bit more responsible in actually figuring out how to discover intelligence. And maybe just neural networks is not the solution. I actually don't believe that the neural networks currently are the solution. And you can see some example data points over here, right? Training a cutting-edge machine learning model can emit as much carbon as 5 cars in their lifetimes. This is just one model, and training it once. And normally you train it thousands of times to get it right. Okay, there are other difficult problems that we have in the world. Public health, clearly, hopefully you have seen it. Genomes, there's a lot of data that we can produce today in genome sequencing machines. If you really want to understand, for example, the cause of diseases, vulnerabilities, how can we have a better life? We really need to understand what this data is. And this is complicated. It's the intersection of biology, genomics, and computing at the same time. And machine learning also plays a role here. And as I said, we have a lot of issues, right? As I mentioned earlier, a memory access consumes 100 to 1000x the energy of a complex addition. So accessing one piece of data element consumes 100 to 1000x energy of adding 2 numbers. You can see the exact numbers over there. These are old numbers, but it doesn't matter basically. The question is, do you really want to move data all around in the world? So let me give you some examples. So motivated by these things, people are doing interesting things. I will go through these relatively quickly just to show you that there's a lot going on in the cutting edge today. This is Intel. It's 2019. It's a bit old now, but this looks like memory, right? How many people have seen things like this? Memory, yeah, these are called modules, memory modules. You plug into your desktop or motherboard. But this is a bit different. This is non-volatile, meaning whenever you turn off the energy, turn off the power, it will not lose its data. So it's more like an SSD at the speed of memory. So this can revolutionize how you actually deal with data. And this is based on a memory technology called 3D X-point, phase change memory. Intel, I think, at some point admitted it, I don't know. But this is new technology that can enable you to actually have much more efficient computers that doesn't lose your data. We will see soon that existing memory technology, DRAM, you need to refresh the data every 64 milliseconds to keep it there, even when it's powered on. When it's powered off, forget about it. Your data is lost. Okay, but this is very different. So this can enable very different things in software as well, and people are working on it. And we've been working on it. Actually, initial architectural ideas. We published this paper in 2009. We did this work when I was at Microsoft Research for 2 years or so. Eventually, we published the paper at this ISCA conference. And we had this vision of actually having this sort of memory replacing existing memories. 10 years later, Intel finally came up with a product, right? So this also gives you an idea of how research works, right? You don't do research just for the next year. You do the research for 10 years, 20 years out there, basically. And if you're interested, you can read these papers. I'm going to basically show you a lot of papers. You're not required to read any of them, but you're welcome to look at them if you're interested in the topic, for example. This is something we've seen. Cerebrus's wafer scale machine learning engine, they basically said that you need a lot of computation and memory at the same time put into a huge chip so that you don't go off chip to bring the data into the chip. And that's the idea. And this is their original version. This is their more recent version in 2021. You can see that it has 2.6 trillion transistors, 46,000 millimeters square. It's almost 60 times the size of this largest GPU today. And if you want to learn more about it, attend the Safari Live seminar on February 28th. It's actually not just this, right? Then they build a system. There are a lot of issues here. You have this huge chip. How do you program it? How do you write a compiler for it? How do you map your machine learning network on it? How do you do the training? How do you do the inference? And then there are other issues like how reliable is it? One of the issues with big chips is there are a lot of faults. How do you actually make sure that it operates reliably? How do you cool it down? This also consumes a lot of power. So how do you cool it down? How do you handle thermals? There are a lot of interesting system issues, and this is, we will talk about that in this live seminar with the chief hardware architect of this machine. This is the processing in memory engine I talked about very briefly, but this is also real. You can see these are also memory modules, right? A little bit different. These are DRAM modules. They're similar to what you have, but they can do processing. You can plug it into your system, and assuming you program it right, you can do processing inside the memory chip without moving data out of the memory chip. And if you're interested, you can read more about it. There are FPGAs you can buy today in the labs here. If you don't know about FPGAs, don't worry. How many people know about FPGAs? Okay, that's good. These are reconfigurable architectures. We'll have an introduction to them next week. But in your labs, you will get to know them very well, for good or bad. You may like them, you may hate them. It'll be up to you, I guess, up to your mindset. But today, with these reconfigurable architectures, you can do acceleration of real applications like genomics, as well as weather modeling, climate modeling. In this paper, we covered that. And you see orders of magnitude performance and energy improvements. Big companies are also looking at processing inside the memories. This is Samsung last year. They basically introduced a processing in memory engine, similar to what we have been working on in the past. I'm not going to go into the details. This is just to, let's say, excite you. We're going to see some of the principles of this internally. So you're going to know about these instructions. So basically, this is a processor, simple processors inside the memory. And they can execute instructions inside the memory without moving data all over the system to a CPU. It can accelerate machine learning computations, according to Samsung. And this is a real chip, basically. So this is an exciting thing that did not happen for decades and decades. It's happening now because energy is a huge problem. People don't want to move data. This is another processing in memory system. You can see you can also buy this and put it on your motherboard. Well, your motherboard needs to be capable of putting it on your motherboard. But this is designed for deep learning recommendation. It's used by Facebook, designed by Samsung. And they can do much faster machine learning recommendations. Again, good or bad, we don't know. Especially with Facebook, you need to be very careful, right? And this is really cutting edge. This is announced, I think, today or tomorrow, maybe even yesterday. I don't know the exact date. Well, this release came about last week. But today they present a paper, or one of these days they present a paper in the Top Circuits conference that talks about accelerated memory. It's a different kind of in-memory computing device, basically. So this is really cutting edge, if you will. Okay, but again, these are ideas that have been floating around in research. We've been working on processing in memory for a decade, more than a decade right now. But these are some example works that we have done. I'm not going to bore you with it, but there are many applications that can benefit. Graph analytics, for example. The recommendation systems, clearly. Mobile devices can benefit. This can benefit from processing inside memory so that you don't move the data between the processor and memory. And energy is a huge deal over here. I'm going to later show you, well, maybe I can tell you. We did this study with Google, actually this paper, published together with Google. We worked with them for 1.5 years or so to understand the applications that are running on their mobile systems, like video processing, like Chrome browser, like machine learning inference, TensorFlow. And we found out that more than 60% of the entire system energy is spent on moving data around. Not computation, not storage of data, just moving data around between the processor and the memory. More than 60% of the energy. That sounds terrible, right? Because the energy cost of data movement is huge compared to computation as well as storage. So you need to be very careful about communicating the data between components of a system. Okay, again, you can look at other works that we have done or others have done on in-memory processing, let's say. Maybe we'll talk about that. And this was the paper that I mentioned that was started as a bachelor's thesis project at ETH, and it was published last year in a top conference that essentially pushes the needle to make this more programmable, basically. How do you make the the processing in memory system much more programmable? Okay, if you're really interested in this, I wouldn't recommend it maybe right now, but I mean, if you're really interested, you can take a look at this overview paper that we have written with my postdocs on processing in memory. Okay, if you're really interested, you can also watch lectures. But we do a lot of work in processing in memory. I'm excited about it. And many people are also excited about it. As you can see, some major companies like Samsung and Hynix. These are there are three major memory manufacturers in the world: Samsung, Hynix, and Micron. And Samsung is the biggest, Hynix is the second, Micron is the third. And two of them are, as you can see, are pushing towards the processing in memory direction. I believe third is also, but they're a bit late. Okay, so that's performance and efficiency. Let's talk a little bit more about performance and efficiency. I've been talking about it earlier also, but there are other examples. This may not be as specialized, but this is in this computer, actually, Apple M1 system on a chip. Many of you may have it also. Some of you who are willing to pay more to Apple probably have the M1 Max that you will see soon. But this is a general purpose microprocessor actually that is for a mobile system on a chip. And you can see that it's complicated. We're going to see different components of it actually in this lecture. But you can see that there are some processors in it. They're called cores. Some of them are high performance. Some of them are less energy efficient, let's call them. There's a GPU. There's a neural engine. There's a machine learning accelerator, basically. There's a vision processor that's not marked here. And there may be other accelerators that are not marked over here. So you can see that it's a heterogeneous system. And there is a lot of memory, caches. We will talk about all of these. You don't need to know any of this right now. Basically, we're going to talk about all of these components as we progress through this course. But the exciting thing is, a company like Apple, which is traditionally a design company and software company, right? They basically said, we're not getting the performance and efficiency out of other stuff that we buy from other people. So we're going to customize our own hardware to the software. Basically, we're going to build our own hardware and customize, because we know what's running on our software. We're going to design our entire stack to be run on this chip. And I think they're doing quite well. In fact, maybe they're doing much better in hardware than in software, because they tend to have a lot of buggy software these days. This is the Max system, if you will, M1 Max. You can see that it's much bigger. So it's exciting. But of course, chips are becoming bigger also. As you want to get higher performance, your chips are becoming bigger. Okay, we talked about Tesla. Again, the same approach. I want to get the highest efficiency and performance, make quick decisions, make the system much better. I design my software and hardware together. Another example here, you've seen this. Cerebras, exactly the same approach. Design my software and hardware together. And software means all parts of the software. Algorithm, compiler. Maybe they modify the language to take advantage of things. System software is modified also. Sometimes the system software doesn't exist if it's an accelerator. The very lightweight software exists. So basically the same approach. Hardware is designed so that they can take advantage of the hardware for their software. This is Google Tensor Processing Unit, as I mentioned earlier, generation 2. So this was designed for machine learning inference. Later, they amplified the capability so that they can do training of the models, formation of the models. This is generation 3, generation 4. You can see architecture is advancing. It's becoming much more capable. In a board, you can get 1 exaflops. Exaflop means exa floating point operations. What is exa? Is it 2 to the 18? No, 10 to the 18? Anybody? I cannot keep track of it after some point. Did you find it? Yes, okay, 10 to the 18, let's say floating point multiplications per second. That's a lot. Okay, so we will see the principles of this. So these are based on, all of these systems are based on some principle, basically. The TPU, Tensor Processing Unit, is based on what's called a systolic array. It's modeled after the human body, let's say. You have the heart and you have the veins, and data flows from the heart to the veins and gets processed along. So we will see this later in lecture 19 or 20 or so, 19, I believe. We will see a lot of actually interesting things about it. Again, at the core of it, there's a systolic array that can do multiplication, mixed matrix multiplication very efficiently, so that you can execute these machine learning applications very efficiently. And the rest is the system design, the software stack that can take advantage of it. And there are many other companies actually building machine learning chips. Big companies, small companies. If you want to do a startup, this is a good time to build your machine learning chip and system, get a lot of money, but you'll be competing with hundreds of other startups. It's a great time, actually. This is, startups in this area are booming today. I will show you in a little picture. Well, this is 2019. This is the AI chip landscape, according to this website over here. In 2021, that became much bigger. In 2022, that's going to become even bigger. So we will see where this is going. The goal is to really make higher performance and hopefully also more efficient chips. Certainly, a lot of people are pushing for higher performance. Efficiency is, in my opinion, extremely important, but maybe it's not pushed as much in this landscape, let's say. Okay, so that was the performance and efficiency. We're going to get back to that in applications. But there are other aspects of computer architecture that are extremely important also. Reliability, safety, security, privacy. I think we all care about that. Like if I want a self-driving car, I really care about all of these, right? I don't want just performance and efficiency from my car. I also want these. That's why pushing the technology in domains like that are extremely important. Maybe I'll give you examples from real life, right? This is a bridge. Does anybody know what this bridge is? Yes? Oh. Not when marching over it, yes, but it's a bridge that collapsed. Yes. This is the Tacoma Narrows Bridge. It's south of Seattle, where I used to live when at Microsoft Research. But this is a bridge that collapsed exactly because of reliability issues. And you would argue that bridges are critical infrastructure, right? For thousands and thousands of years, humanity has built bridges. And humanity was actually very careful in defending their bridges at the war times, for example. And it's critical infrastructure. If there's a bit flip in this bridge, meaning if the bridge actually falls, then you have a reliability problem, security problem, safety problem. If some people are marching on it, then you have a serious safety problem. In this particular case, there was no one marching on it, but there were other bridges where people were marching on it or were doing whatever. So this is what happened to this bridge. 1940. It's called the Galloping Gertie. There's a lot of video. There's actually a video of this falling down also, because it was expected. I mean, something was wrong with the bridge. It was doing this because of aerostatic flutter, and as a result, at some point, it collapsed. They couldn't fix it. That's another view. But basically, this is a fundamental problem. If you think bridges are important infrastructure, then you should think that computers are even more important, because computers are a lot more common everywhere. They're going to be even more everywhere. They're going to be making decisions for us. Bridges are not important. I will argue, relatively, right? Relatively speaking, they're not important, but computers are everywhere. And there's another bridge, right? These people are very happy right now, but if something small happens in that bridge and they fall down, they're not going to be happy next minute. So I think security overall is about preventing unforeseen consequences, in my opinion. And we need to really take a fundamental approach to security so that we don't run into these problems. If your self-driving car has an issue and someone can take over it, that's not good. If it's a reliability issue, like one bit goes wrong, you stored one data element and that data element changed for whatever reason, as we will see, then your self-driving car may not behave as expected. So this is example. Then the question is, how safe and secure is this platform, right? Can you trust it like Mr. Bean trusts it? So how many people have heard about RowHammer? Okay, now you'll learn more about it because this is something that my group has discovered together with Intel in 2012, but we wrote the first paper in 2014. And essentially, I would consider that the cause of this bridge's fall going into the future, of course, not in the past. So the idea is here, you have these memory chips, and you can predictably induce bit flips on these commodity memory chips that are manufactured by 3 major manufacturers that we talked about and more. Basically, if you store some data elements, you can corrupt that data element, change a 1 to a 0 or 0 to a 1 in a predictable manner. And many chips are vulnerable. It's really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability, also a reliability and safety vulnerability, clearly, as you can imagine. And people are writing, inspired by RowHammer, articles like this. Forget software, now hackers are exploiting physics, which I think is actually a good high-level characterization. So I'll give you the problem very quickly. We'll talk about it a little bit more in the next lectures, but just to give you an overview. But basically, you don't need to understand anything except the fact that a memory consists of these rows, and data is stored in each row. And whenever you access a row, you do this. Apply high voltage to the data. And then you apply low voltage so that you can access some other thing. Now, if you keep doing this repeatedly, high voltage, low voltage, accessing repeatedly one row of data, it turns out physically adjacent rows of data are vulnerable. Why? Because they're physically too close. So whenever you're doing this accessing to a row, these poor rows that are next to you are too close to you that the action you're taking with high voltage is affecting them. This is called electromagnetic coupling. In an electromagnetic way, you're coupled to the next row. So if data, for example, somebody else stored some data over here, you corrupted their data because some bits turned from 1 to 0 or 0 to 1. That's the idea over here. We'll go into a little bit more detail later on. But this should not happen clearly, right? Whenever you access some data, you should get that data. That data should be correct, and everything else should not change, right? That's how it should work. Now you're breaking some fundamental level of trust in your hardware. The hardware is not giving you that guarantee. The hardware, if you keep accessing a row, some other rows get corrupt data. How do you deal with it? Well, it's very difficult to deal with it because you have no idea what rows will get corrupt. And well, this doesn't make sense, right? Things should not get corrupt if you're accessing one location. That's it. Unfortunately, they're happening today because cells are too close to each other. Memory is basically, we packed a lot of memory into one space. Okay, so basically you can see that there are a lot of errors that you can induce and one can take over an otherwise secure system. Again, I'm not going to go over this in detail right now, but somebody can take advantage of these bit flips to take over your system completely. And if you're interested, you can read our paper as well as Google's papers on this topic. Okay, I'll skip this, maybe we'll talk about it later. But there are a lot of works that actually show that if you can flip a bit in your memory, meaning it was 1, it became a 0, or it was 0, it became a 1, you can do many security tricks, meaning you can gain unrestricted access to systems of website visitors. You can gain control of a smartphone. You download an application that does this bit flips and takes over your phone. Now, you may not even know it, right? Unless they expose it to you. You can do it with GPUs. Okay, I'll go through this relatively quickly. There's a lot of exciting things. But one thing that's really interesting here is these folks more recently, last year, published this paper. You have a neural network that is good, reasonably good, accuracy 90%. I wouldn't call that good, but they tested that neural network and it was reasonably good, 90%. It can predict things reasonably well. But if someone goes in and exercises these bit flips, meaning calls these bit flips using RowHammer, your accuracy goes down to 10%. Now you question, right? I built this neural network. I've spent a lot of carbon on training this model. And in the end, somebody with bit flips destroying all my accuracy. Maybe I should rethink what I'm doing, right? So this is how important security, reliability, and safety is. Everything else you do is dependent on this. If you're not secure, reliable, and safe enough, if you not provide some basic trust to the underlying hardware, you cannot get any of the benefits. As a result, this question, in my opinion, is no. Can we depend on computers in these situations? I don't think so. If you want to depend on them, do it at your own risk. So, okay, there's a lot of work in this area also. You can see we've written a retrospective paper, but there's a lot more research that has been done. It's getting much worse. Existing solutions do not work. It's hard to guarantee chips that provide the guarantee that we like. And it has many dimensions, and industry adapted solutions don't work. And we're also trying to solve the problem. I believe we can solve it, but it takes effort, basically. It's not an easy problem, let's say. Okay, so you can learn more about these while you're sleeping if you're interested. There are other security issues like meltdown and Spectre. How many people have heard about this? Okay, more people. Well, similar people. If I asked this question in 2018, almost everyone raised their hands. I guess they're not as popular today because these were discovered in 2018. But basically, someone can steal secret data from your system, even though your program and data are perfectly correct. Your hardware behaves according to the specification, and there are no software vulnerabilities and bugs. How can it happen? Well, we'll learn about it. Maybe we'll talk about it in the next lecture, but it's a sophisticated attack. I don't expect you to understand everything. It's a side channel attack. There's some data that's in your cache inside the processor, and someone can figure out your secret keys by inspecting that data in a roundabout way. That's why it's a side channel. You cannot get access to the data, but you can get access to what the data may be based on a side channel. If you don't understand that, don't worry about it. But this is a vulnerability, and it's a privacy and security vulnerability. And this is another example. Okay, there are more demanding workloads today. This is a figure that I kind of mentioned, right? There's an exponential growth of neural networks that's happening. You can see that the need for computation has grown by 1800x in the cutting edge of neural networks in just 2 years. And that's why people are building these accelerators that we discussed. There's a reason why people are looking into this. You can also question, is this the right way to go? And my general answer would be probably we should be rethinking how we do machine learning in general, because I don't think this is sustainable, even if you're throwing the most efficient accelerator to it. But basically, soon you will have multi-trillion parameter machine learning models, which are very difficult to deal with, even in the most efficient hardware. So basically, people are dreaming and applications are coming. As applications push boundaries like this, machine learning is one example, computing platforms will become increasingly constrained. And Another example is genomics. This is a genome sequence analysis, a genome sequencing engine. You can sequence your genome for relatively cheap with this machine. But you can produce a lot of data, but you cannot process it basically today. And these machines were actually used. This was one of the last pictures that I showed in person 2 years ago in this class, talking about these machines and how they're being sent all over the world so that they can understand the coronavirus. And they were actually extremely helpful in understanding coronavirus. So we really need to take advantage of these machines, but we have a problem with the data today. We can actually do a lot of other things like understand the disease spread and what kind of diseases, what kind of mutations can come about, what kind of variants can come about. If you actually do this as a massive scale, population scale, and city scale, people have done a lot of studies actually in New York City, for example. People have used similar infrastructures, a little bit older, as you can see, for the surveillance of Ebola outbreak. Today, COVID-19 is also helping this technology develop, but I think maybe we should be investing more into this. And we have high throughput genome sequencers. These are all data generators, basically. They can generate lots of data. If you put them data, like put them any sample and they will generate data for you. They will sequence genomes. The question is, what do you do with that data? And you can see an example of how many genomes are being sequenced yearly. So basically today, scientific discovery and medical advancements is really bottlenecked by our computers, computing platforms. How well can we design our computing platform so that we can actually take advantage of the data that's being generated? As a result, again, people are designing specialized accelerators, and we have been doing it in our research. So software acceleration is important. We've been doing FPGA-based acceleration, which we may briefly talk about later. We've been doing in-memory acceleration of DNA sequence analysis, and there are algorithm architecture co-designs for DNA sequence analysis. Again, I don't expect you to know all of these, but the idea is to show you that there's a lot of systems that are being built to do genome analysis today. And the future is very bright, in my opinion, here, but we need to design systems to take advantage of it. COVID-19 is interesting. I thought people may be interested in it, but people are actually doing that for COVID-19 also. Again, the details you can read about if you're interested. People are designing systems to take advantage of these hardware that can sequence genomes really fast. Okay, if you're interested, if you're really excited about genome analysis, and if you want to read only one thing, you can read this short paper that we wrote. And there's a lot more over here. So clearly there are more demanding workloads here. This is probably a good place to stop, actually. We're almost at the end. If there's any question, I will take it. But I've given you a lot of workloads right now, a lot of ideas, hopefully, and a lot of the reason why systems are becoming much more interesting and complex. Tomorrow, we'll take it from here. All right, take care.